Hello everyone, welcome back. In this video, we're going to talk about finding the areas between curves. So suppose that we have two functions, y equals f of x and y equals g of x, and that we're interested in the area which is bounded between the two functions. So how exactly do we determine this area? Well, one approach is to approximate the area by using Riemann sums. So we subdivide the interval from a to b into equal subintervals that have a width of delta x. Then the heights of each of these rectangles is given by the difference between the two function values. So it's the difference f of x of I minus g of x of I. We can then find the exact area by taking the limit of the Riemann sums, so letting n go to infinity, where n is the number of subintervals or the number of rectangles. Now we can recognize this limit of Riemann sums as the definite integral of f of x minus g of x. And so the area that's bounded between the two curves, y equals f of x and g of x, where f of x is greater than or equal to g of x for all of x in our interval, is given by this Riemann sum, and this can be written as a definite integral from a to b of f of x minus g of x. So in other words, if f of x is greater than g of x on the interval from a to b, then to find the area of the region that is bounded between the two curves, we take the difference between f of x and g of x, and then integrate from the interval from a to b. So let's have a look at example 1. Let's find the area of the region that's bounded by the curves y equals x squared and y equals 2 minus x squared. So we'll first draw the regions that we're interested in. So y equals x squared is the parabola, where the vertex is at the origin. And y equals 2 minus x squared is also a parabola. It will open downwards, and it has a y-intercept at 2. And so the region that's bounded between the two curves is this shaded area here. So now the first thing that we need to determine is the interval of integration. So to find the region, we want to determine the points of intersection. So where do these curves intersect? And to determine their points of intersection, we're going to equate their functions. And so what we end up with is that we're solving the equation where x squared is equal to 2 minus x squared. So they have the same y coordinates. And so solving this equation will tell us the x coordinates of where they intersect. So if we solve for x squared, we get 2x squared is equal to 2, which means that x squared is equal to 1. So x is plus or minus the square root of 1. which is plus or minus 1. And so this tells us that the points of intersections occur when x is minus 1 and when x is positive 1. So to determine the area of the region, we're going to integrate from a to b, and then take the difference between f of x and g of x. Now f of x is going to be the upper function, and g of x is the lower function. So if we look in our sketch, what we see is that the upper function is the parabola y equals 2 minus x squared. So this is what we will call our f of x. And the lower function is the parabola y equals x squared. And so this is what we will call g of x. And so the area is going to be the integral from -1 to 1 of 2 minus x squared minus x squared. And simplifying, we get the integral from -1 to 1 of 2 minus 2x squared dx. So now we can use the fundamental theorem to evaluate the integral. So the antiderivative of 2 is 2x, and the antiderivative of 2x squared is 2x squared over 3. And we evaluate at 1 and -1. So substituting 1, we get 2 times 1 minus 2 times 1 cubed over 3. And we subtract the lower limit, which is 2 times -1 minus 2 times -1 cubed over 3. So this becomes 2 minus 2/3 minus -2 plus 2/3. And so making a common denominator of 3, we get 6 minus 2 all over 3 minus -6 plus 2 all over 3. So that's 4/3 minus -4/3, which simplifies to positive 8/3. And so the area of the region that's bounded between these two curves is 8 over 3 squared units. So now let's jump to number 3. Let's find the area of the region that's bounded between y equals e to the x, bounded below by y equals x, and between the lines x equals 0 and x equals 1. So we have the exponential function y equals e to the x. And then we have the line y equals x. And then we have the lines x equals 0 and x equals 1. So that is the y-axis and the line x equals 1. And so the region that we're interested in is this shaded area. And so to determine the area, we need to determine our limits of integration, as well as the functions f of x and g of x. So the upper function is going to be the exponential. So this is what we will call f of x. And the lower function is the line y equals x. And so that is what we will call g of x. And we're going to integrate between 0 and 1. So the area is given as the integral from 0 to 1 of e to the x minus x dx. So now let's evaluate the definite integral using the fundamental theorem. The antiderivative of e to the x is e to the x. The antiderivative of x is x squared over 2. And we evaluate at the upper and lower limits. So we have e to the 1 minus 1 squared over 2 minus e to the 0 minus 0 squared over 2. So we end up with e minus a half minus e to the 0, which is 1, minus 0. And so that gives us e minus a half minus 1, or e minus 3 halves. So next, let's have a look at 4a. So we want to find the area enclosed by the given curves. So we have the curve y equals the sine of x, y equals x equals pi over 2, and x equals pi. So let's first sketch the region. So we have the function. So we have the function y equals the sine of x. And the line y equals x. As well as the vertical lines, x equals pi over 2, and x equals pi. And so the region that we're interested in is going to be this shaded area here. And so to find the area, we will determine the integral from a to b, f of x minus g of x dx. So our limits of integration, we're going to integrate between pi over 2 and pi. The upper function is the line y equals x, so we'll call this f of x. And the lower function is going to be the sine function, so we'll call this g of x. And so the area is the integral from pi over 2 to pi of x minus the sine of x dx. And so now, evaluating the definite integral, we look for the antiderivative. So that's x squared over 2 minus negative cos, and we evaluate at the endpoints at pi and pi over 2. So simplifying, we have x squared over 2 plus cos and now we substitute pi into the antiderivative, so that's pi squared over 2 plus the cos of pi minus pi squared, or pi over 2 squared all over 2 plus the cos of pi over 2. So we get pi squared over 2 minus 1 minus pi squared over 8 plus 0. So here we can make a common denominator of 8. So that gives us 4 pi squared over 8 minus 8 over 8 minus pi squared over 8. And this will simplify to 3 pi squared minus 8 all over 8. Let's have a look at letter C. We have y equals the square root of x minus 1 and y equals x minus 1. So let's first draw the region. So the root of x minus 1 is the upper half parabola, and the line x minus 1 is this line here, and the region that's bounded between them is going to be this shaded region. And so the first thing we need to determine are the points of where they intersect, and that will give us our limits of integration. So to find our points of intersection, we're going to set the functions equal. So we have x minus 1 is equal to the square root of x minus 1. So they have the same y coordinates. And now we solve the equation for x. We're going to square both sides. And we get x minus 1 squared is equal to x minus 1. And now we FOIL the left-hand side. We get x squared minus 2x plus 1 is equal to x minus 1. So here we're solving for a quadratic. We're going to move all of the terms to the left-hand side. So that's x squared minus 3x plus 2 is equal to 0. And this can be factored to x minus 1 times x minus 2. And so this allows us to solve for x. We get that x is either 1 or 2. And so this tells us that the points of where they intersect is at 1 and 2. So now we'll also determine the upper and lower function. So the upper function is the square root of x minus 1. So we'll call this f of x. And the line x minus 1 is the lower function, which we will call g of x. And so the area is the integral from 1 to 2 of the square root of x minus 1 minus x minus 1 dx. So let's simplify. We can distribute the negative through the brackets. So we have the integral from 1 to 2 of the square root of x minus 1 plus 1 minus x. And we can use the properties of the integral to separate this into two separate integrals. So we have the integral from 1 to 2 of the root of x minus 1 dx plus the integral from 1 to 2 of 1 minus x dx. So to handle the left integral, we will use a substitution. We'll let u be x minus 1. So du over dx is equal to 1, which means that du is equal to dx. So we substitute this into our integral. We have the integral from x equals 1 to x equals 2, u to the 1/2 du. So now we can find the antiderivative. We have u to the 3/2 divided by 3/2 evaluated at x equals 2 and x equals 1 plus the antiderivative of 1 minus x, which is x minus x squared over 2, and we evaluate it at 2 and 1. Now let's substitute back the original variable and simplify the coefficients. We have 2 over 3, x minus 1 to the 3 over 2. We evaluate this at 2 and 1. Substituting 2 into the antiderivative, we get 2 over 3 times 1 to the 3 over 2. When we subtract the evaluation at the lower limit, so 2 over 3 times 0 to the 3 over 2. And then we add this to the evaluation of the other integral. We have 2 minus 2 squared over 2. And we subtract the evaluation at the lower limit, which is 1, minus 1 squared over 2. And now simplifying, we get 2/3 minus 0 plus 2 minus 2 minus 1 minus 1/2. So this will simplify to 2/3 minus 1/2. And we'll make a common denominator of 6. So that's 4 over 6 minus 3 over 6, which is 1 over 6. Now let's jump to letter E. We have y equals 2x minus x squared. Y equals 2x minus 1, and the lines x equals 1, negative 1, and x equals 2. So let's first sketch the region. So the function 2x minus x squared is the parabola which opens downwards. And the line 2x minus 1 is the line that passes through the curve And so the region that's bounded between -1 and 2 will give us two regions. So we have this shaded area here and this shaded area. And so we'll call each of these areas as A1 and A2. So we'll first look for the points where they intersect. So we'll find the points of intersection by equating the functions. So we have 2x minus 1 is equal to 2x minus x squared. So let's move all of the terms to one side. So that gives us x squared minus 1 is equal to 0. And we can solve for x squared. So that gives us x squared equals 1. And x equals plus or minus the root of 1. So x is plus or minus 1. And so that tells us that the x-coordinates of their points of intersection is at -1 and +1. So now to determine the area of the regions, we will look at finding the area of A1 and then adding it to the area of A2. Now to determine the area of A1, we will integrate between 0 or -1 and +1, and we will take the difference between the upper and the lower functions. So in this region, the upper function is the parabola 2x minus x squared, and the lower function is the line 2x minus 1. So this is the integral for calculating A1. Now to calculate the area for A2, we're going to integrate between 1 and 2. And now in this region, the upper function is 2x minus 1, and the lower function is the parabola 2x minus x squared. So now let's simplify. We have the integral from -1 to 1 of 1 minus x squared dx plus the integral from 1 to 2 of x squared minus 1 dx. So now we can find the antiderivative. So we have x minus x cubed over 3 evaluated at 1 and -1 plus x cubed over 3 minus x evaluated at 2 and 1. So we substitute our upper and lower limits. We get 1 minus 1 cubed over 3, subtract -1 minus -1 cubed over 3, and we add this to 2 cubed over 3 minus 2 minus 1 cubed over 3 minus 1. So now let's simplify. We have 1 minus a third minus negative 1 plus 1/3 plus 8/3 minus 2 minus 1/3 minus 1. So this will simplify to 2/3 minus negative 2/3 plus, we'll make a common denominator of 3. So that's 8/3 minus 6/3, which simplifies to 2/3 minus negative 2/3. And this will give us 4/3 plus 4/3, which gives us 8/3. Now let's jump to G. We have y equals the cos of x, y equals 1/2, x equals 0, and x equals pi. So let's draw the region. So cosine looks like this. And we have the line y equals 1/2. And we have the lines x equals 0, which is the y-axis, and x equals pi. And so the area that we're interested in is going to be these regions. And so the first thing we'll look for is the point of intersection. So we'll set the cos of x equal to 1/2. And so we want the angle, which makes the cosine equal to 1/2. And the angle is between 0 and pi. And so this happens when x is pi over 3. So this x coordinate is pi over 3. So now we will divide the area into two integrals. So we'll call this A1, and this region will be A2. And so the area of the regions is given by A1 plus A2. And to find the area for A1, we're going to integrate between 0 and pi over 3. The upper function is cosine. The lower function is the line 1/2, y equals 1/2. And then we'll add it to the area of the second region. So we'll integrate between pi over 3 and pi. This time the upper function is 1/2 and the lower function is cosine. So now we can evaluate the definite integrals. So the antiderivative of cosine is sine minus the antiderivative of 1/2, which is negative 1/2 x. We evaluate at pi over 3 and 0. Then for the second integral, we have 1/2 x minus the sine of x, evaluated at pi and pi over 3. So now we'll substitute the upper limit. We have the sine of pi over 3 minus 1/2 times pi over 3. We subtract the evaluation at 0. So the sine of 0 minus 1/2 times 0. Then we add it to the evaluation of the other antiderivative, which is 1/2 pi minus the sine of pi. And we subtract 1/2 times pi over 3 minus the sine of pi over 3. Now the sine of pi over 3 is root 3 over 2. Then we have minus pi over 6 minus 0 plus 1/2 pi minus pi over 6 minus root 3 over 2. So we have root 3 over 2 minus pi over 6 plus 1/2 pi minus pi over 6 plus root 3 over 2. And simplifying, we have root 3 plus 1/2 pi minus 2 pi over 6. So let's make a common denominator of 6. So that gives us 6 root 3 plus 3 pi minus 2 pi all over 6. So that's 6 root 3 plus pi all over 6.